The first of three essential questions. What is the process of sea floor spreading? Please fill out the top of your note page under where it says essential question. What is the process of sea floor spreading? Let's start with a definition. Plate tectonics. Plate tectonics is the theory, and this theory describes the movement and recycling of segments of Earth's crust throughout time. As you copy this down, let me remind you that Earth's crust is not one solid piece. Rather, it is separated into tectonic plates that are constantly moving together and apart. We call this phenomenon plate tectonics.
Whether studying earthquakes or other geologic events, scientists usually focus their attention on plate boundaries.
The boundaries of the plates are where we have the active deformation. So that's where we have the active mountain building or the active basin subsidence, the active faulting that produces the earthquakes that are damaging to populations. It's where we have the active volcanoes. So it's intimately tied into the whole issue of those sorts of natural hazards for the global population.
When they're moving, plates can be drifting apart, coming together, or slipping past each other. The three types of boundaries that result from these interactions are called divergent, convergent, and transform boundaries, depending on the nature of the plate motion.
Well, if we start at the beginning, we have divergent plate boundaries, areas where the lithosphere literally is being rifted apart, and we have new seafloor filling up that void and allowing the seafloor to spread. There's lots and lots of geographic examples, and the most obvious one is the mid-ocean ridge system. This is the area where you have these high mountain chains, you have the lava welling up along those rifts, and the seafloor actively spreading. They also occur on the continents as well, however. If we look at probably the classic continental example, we look at East Africa, we have an example where the African continent is literally being broken up along the East African Rift Zone, the Gulf of Aden, and also the Red Sea. These are areas where the continent is literally breaking up, and we see new seafloor growing in these areas. In the United States, we have what's referred to as the Rio Grande Rift, where the area of the Rio Grande is actively opening up. And Albuquerque actually sits right in the middle of what would potentially someday become a small ocean basin.
The spreading centers are extremely important tectonically because they produce most of the world's volcanism, even though you don't see that because it's all underwater except for rare places.
While volcanoes can be very dramatic, the most striking result of seafloor spreading is probably what occurs over the long haul.
If you start off with a narrow rift system and there's seafloor spreading going on after millions of years, you'll end up with a really big ocean. That's what happened in the Atlantic Ocean. It took it 180 million years or whatever, but that's how the ocean basins get built, by seafloor spreading at the mid-ocean ridges. For the rate of plate movement, we often give people the analogy of how fast your fingernails grow, which seems pretty slow. It's a few centimeters a year, and it depends on which boundary you're talking about.
The East Pacific Rise Mid-Ocean Ridge Spreading Center forms it very fast. Mid-Atlantic Ridge forms it very slowly. You're moving plates apart on the order of centimeters per year, and that requires that you form this crust continuously. It's formed at different rates in the past. 100 million years ago during the Cretaceous, it formed 2 or 3 times faster than it is now. It seems to have slowed down a little bit now.
If we look at convergent boundaries, where the one piece of lithosphere is diving underneath another, we have all of the world's largest mountain chains, really. We look at, here in North America, we have the Cascades, where we see active subduction of the Juan de Fuca plate underneath North America. As that plate dives down, generates large earthquakes, and we also have the volcanism associated with it. And at the surface, we have this deep sea trench.
The subducting plates are so heavy they're actually being pulled into the earth by their own weight. And right at the top, there's a big trench there. Those are the deepest places in the ocean. It's right where the plate's being pulled down. It's actually being held down against its will. If you would just cut off that sinker that's pulling it down, it would actually float back up and fill in the trench.
If we work our way down to South America, the Andes Mountains. The Andes are the result of this subduction. If we work our way over to the Western Pacific, we have Japan. The island of Japan sits right over one of these subduction zones as a result of the volcanism and the earthquakes there. The Philippines. All of these are examples of that subduction process. Then, lastly, we have what we refer to as transform boundaries, where we have one piece of lithosphere simply sliding by another one.
The transform faults under the oceans can have earthquakes on them. They don't usually have volcanism on them. They're better known to us in continental settings. For example, the San Andreas Fault is the transform fault between the Pacific Plate and the North America Plate in in California. And there's a similar fault like that between the Australia Plate and the Pacific Plate in the South Island of New Zealand. So those settings can also have big earthquakes.
And basically, the three types of plate boundaries, the ridges, the transform faults, and the trenches, each have a topographic expression.
If we go to the ocean basins, we see the massive mid-ocean ridge system, basically a large 10,000-foot high mountain chain which completely runs down each of the major oceans in the world. And this mountain chain is almost entirely volcanic, and it is really where we see the seafloor actively opening up.
The transform faults are scars in the earth where the plates slide past one another. They're deep topographic expressions. You have a lot of earthquakes there. And then the trenches are deep areas where the plates are getting subducted back into the planet. The subduction zone depths can go up to, trench depths can go up to about 6 kilometers.
Next definition, lithosphere. The lithosphere is the part of Earth which is composed mostly of rocks, meaning the crust and the outer mantle. As you finish copying this down, let me remind you that the lithosphere is the outer part of Earth. It's about 62 miles deep, and it includes the crust and upper mantle. We live on the part of the lithosphere that we call continents.
The outermost surface of the Earth is covered with a rigid shell called the lithosphere. The lithosphere is made up of the crust and the upper mantle, which is broken up into about 30 tectonic plates. 7 of these are major plates: the North American, South American, Eurasian, African, Indian, Pacific, and Antarctic plates. The others are smaller, like the Juan de Fuca plate in the northwestern United States.
Next definition, seafloor spreading. Seafloor spreading is the process by which new oceanic lithosphere forms at mid-ocean ridges as tectonic plates pull away from each other. As you finish copying down this definition, let me remind you that mid-ocean ridges are divergent plate boundaries at the bottom of Earth's oceans. A mid-ocean ridge consists of a deep valley surrounded by a long mountain chain on either side. New oceanic crust is created at mid-ocean ridges. And our last definition for this lecture, mid-ocean ridge. A mid-ocean ridge is an oceanic rift zone that consists of long mountain chains with a central rift valley, which is a divergent boundary. As you finish copying down this definition, let me remind you that mid-ocean ridges are oceanic rift zones. Mid-ocean ridges are divergent plate boundaries at the bottom of the ocean. On either side of a mid-ocean ridge, you will find long mountain chains. In the left-hand column, let's set up our first heading for this lecture, sea floor spreading. please write in your left-hand column, sea floor spreading. Earth's crust and the upper part of the mantle make up the relatively cool, rigid outer layer of the planet. This cool and rigid layer is called the lithosphere. The lithosphere is separated into tectonic plates. These tectonic plates are constantly moving together and apart. This phenomenon is known as the theory of plate tectonics. This theory of plate tectonics explains how Earth's surface is recycled over time. Plate movements are responsible both for the formation of certain features on Earth's ocean floor and continental crust, and, to a lesser extent, the distribution of Earth's rocks and minerals. Tectonic plates are destroyed at subduction zones. Subduction zones are areas where a denser plate slides beneath a less dense plate. The denser plate then melts into Earth's mantle. New oceanic crust is formed at mid-ocean ridges. This happens through the process of sea floor spreading. Mid-ocean ridges are oceanic rift zones. They consist of long mountain chains along a central rift valley. Mid-ocean ridges are divergent plate boundaries. At mid-ocean ridges, tectonic plates move apart, and sea floor spreading occurs. Sea floor spreading is the process by which new oceanic lithosphere forms at mid-ocean ridges. As tectonic plates move further away from each other, magma rises from Earth's interior. It then cools and solidifies in the center of the ridge. The rising magma pushes up between the plates and drives them further apart. As new crust is forming at the spreading center, it pushes the older crust apart, and because of this, the oceanic crust contains symmetrical patterns of crustal rock ages. These rocks increase in age as their distance from the mid-ocean ridge increases. Please insert your second heading in the left-hand column. This new heading in the left-hand column is Learning from Mid-Ocean Ridges. Again, your new heading in the left-hand column should be Learning from Mid-Ocean Ridges. The patterns that form at mid-ocean ridges reveal additional information about Earth's history at the time the older crust was formed. For example, Earth's magnetic field occasionally reverses its polarity. Earth's magnetic field is generated by the flow and circulation of the liquid outer core and the solid inner core. But this field is not static. It moves all the time. For this reason, magnetic north and true north, meaning the north end of Earth's rotational axis, do not always correspond. True north is a fixed geographic location, but magnetic north is what attracts the needle in a compass. Magnetic north migrates over time in a phenomenon called polar wandering. So magnetic north does not always match up with true geographic north. The angle of this difference at any given location, meaning the difference between magnetic north, for example, and true geographic north, is called declination. The declination can be set on a compass to correct for this difference, and maps often indicate it as well. Now, polar wandering is a continuous process that occurs even on a human timescale. Magnetic north has shifted several degrees within a period of just a few decades. In addition to the poles wandering over the northern and southern hemispheres, Earth's magnetic poles also completely flip. Throughout geologic history, Earth's magnetic field has completely reversed many times. When Earth's magnetic field reverses polarity, the same end of the compass needle still points to the magnetic North Pole. However, the magnetic North Pole would be located closer to the geographic South Pole. After yet another pole reversal, the poles switch back so that magnetic north is again closer to geographic north. These reversals have happened many times throughout Earth's history, but they do not happen at a predictable rate. Over the last 20 million years, there has been a magnetic pole reversal on average of about every 200,000 to 300,000 years. However, much longer periods have passed without any pole reversals. Scientists can study these magnetic pole reversals by studying the magnetic polarity of rocks in Earth's crust. Spreading centers, like in seafloor spreading, are the ideal place to study this phenomenon because rocks on either side of a mid-ocean ridge can be matched and correlated. The oceanic crust contains symmetrical bands of alternating magnetic polarity on each side of mid-ocean ridges. Scientists are not exactly sure what the effects of a magnetic field reversal would have on living things. However, it is unlikely that a reversal would be harmful to most life on Earth. Although Earth's magnetic field protects the planet from solar radiation, the atmosphere also protects the planet from the sun's harmful rays. Animals that rely on magnetic fields for navigation and migration would likely be able to adapt since pole reversals seem to occur very slowly in relation to an individual lifespan. At this point, you should be able to answer today's essential question. So in your summary box at the bottom of your set of notes, please write your answer to the question, what is the process of sea floor spreading?